Okay, so we already know how AI stores information using vectors. We know that every word, every pixel, and every sound is turned into a list of numbers floating in an abstract mathematical space. But just storing info, that's not enough. A brain full of neurons that never fire isn't really thinking, right? The real magic begins the moment those vectors actually start interacting. Welcome to this explainer. Today we're diving right in to demystify artificial intelligence by proving that its so-called intelligence actually boils down to the literal, basic arithmetic of vectors.
Here's our agenda for today. We're going to cover adding vectors in 2D and 3D, vector subtraction, scalar multiplication, linear combinations, GPT vector math, and wrap it all up with some actual PyTorch code and tensors. All right, let's kick things off with Section 1, adding vectors in 2D and 3D. So what is vector addition? It simply means adding matching components together to combine information. Now, geometrically, you might know this as the head-to-tail rule, taking a second arrow and starting it right from the tip of the first one. But mathematically, it is incredibly straightforward. You literally just line up the x components and the y components, and you add them straight down. Let's actually put this into practice and look at the numbers. For our first example, we've got the vector 3, 2, and we are adding the vector 1, 4. So we take 3 plus 1, which gives us our new x of 4. Then 2 plus 4 gives us our new y of 6. Our resulting vector is exactly 4, 6. And hey, even with negative numbers, the rule holds perfectly. Look at our second example. 5 plus a negative 3 cleanly yields 2. Then for the y-coordinates, negative 2 plus 6 gives us 4. So the final result is just 2, 4. See, it really is that simple.
And this exact same rule applies in 3D space. Heck, it applies in 12,000 dimensional space for that matter. You just add the matching components across every single axis. Let's walk through it. Here, we're adding the vector 2, 1, 3 to the vector negative 1, 4, 0. Combining the x components, 2 plus negative 1 gives us 1. Then for y, 1 plus 4 bumps us up to 5. And finally, mapping the z-axis, 3 plus 0 just stays at 3. So our final combined vector is 1, 5, 3. Literally, no matter how many dimensions you have, you just match them up and add.
Moving right along to Section 2, vector subtraction, which is all about finding the difference.
If addition is all about combining concepts, well, subtraction is about finding the exact difference in direction from one point to another. Instead of adding, we're going to subtract the components straight down. What this does is yield a displacement vector. Think of it like the exact physical path you would walk to get from the second point back to the first point. It's kind of like Google Maps for math.
Let's take a look at the arithmetic here. For our first set, we have 5, 7, minus 2, 3. Doing the math, 5 minus 2 equals 3, and 7 minus 3 equals 4. So, our resulting displacement is 3, 4. Now, our second example shows exactly what happens when we subtract larger values. We start with 4, 1, and we're subtracting 6, 5. So 4 minus 6 is negative 2, 1 minus 5 is negative 4. This yields a negative directional path of negative 2, negative 4. This very simple idea of subtraction revealing direction, that is exactly how AI models learn the underlying relationships and distances between words.
All right, on to Section 3, scalar multiplication, or how we go about scaling vectors.
So, we know how to combine vectors, and we know how to find the difference between them. Now we need to know how to scale them. Scalar multiplication scales our vectors using a single magnitude. To actually do this, we just distribute our single number, which in math we call a scalar, into every single component of the vector.
What's truly fascinating here is the contrast between positive and negative scalars. For positive scalars, we're stretching and shrinking. Multiplying our base vector of 2, 3 by the scalar 3 gives us 3 times 2, which is 6, and 3 times 3, which is 9. The vector stretches out to 6, 9. Now, multiplying by 0.5 shrinks it. Half of 2 is 1, and half of 3 is 1.5, giving us 1, 1.5. But look at the negative scalars. Multiplying by negative 1 physically flips the direction. Negative 1 times 2 is negative 2, and negative 1 times 3 is negative 3. And if we multiply by negative 2, it flips it and stretches it, giving us negative 4 and negative 6.
Let's turn to Section 4, linear combinations, and how we use them for building new vectors.
Now we're going to mix our first two concepts together into what's called a linear combination. This allows us to build almost any new vector out of really simple building blocks. In step 1, we scale our input vectors. We have 3 times the vector 1, 0, and 5 times the vector 0, 1. In step 2, we just distribute those scalars to get our raw numbers, giving us 3, 0 plus 0, 5. And finally, in step 3, we just add them together to lock in the pieces. 3 plus 0 is 3, 0 plus 5 is 5. We land perfectly at the newly combined coordinates of 3, 5.
The really crucial point here is that this works beautifully even with negative scalars. Let's walk through this next example. Step 1. We want to combine 2 times the vector 2, 1 with negative 1 times the vector negative 1, 3. Step 2. We distribute. 2 times 2, 1 becomes 4, 2. And for the second part, negative 1 times negative 1, 3 flips the signs to become positive 1, negative 3. Step 3. We just add them straight down. 4 plus 1 is 5, 2 plus negative 3 is negative 1. By stretching and adding, we've constructed an entirely new vector, 5, negative 1.
Okay, Section 5, GPT Vector Math, and how these exact operations work inside AI.
Having survived the mathematical gauntlet, let's actually look at large language models. Every time you send a prompt to an LLM, the AI translates your text into a token embedding, and it translates its location in the sentence into a position embedding. And then, it simply adds them up to lock in the meaning.
Let's look at a real numeric embedding sum. We have our token vector, 0.8, negative 0.2, 0.5. And we have our position vector, 0.1, 0.3, negative 0.4. We literally just add them straight down. 0.8 plus 0.1 creates 0.9. Negative 0.2 plus 0.3 is 0.1. 0.5 plus negative 0.4 is 0.1. Boom! This single resulting vector, 0.9, 0.1, 0.1, now mathematically represents both what the word means and exactly where it sits in the sentence.
And it totally doesn't stop there. As data flows through the neural network, it uses what's called a residual connection. This literally takes the new layer output and adds it directly back to the old hidden state to preserve information. Let's do the math on this one. The old hidden state is 1.2, 0.4, negative 0.6. The new layer output is 0.3, negative 0.1, 0.2. Add them together. 1.2 plus 0.3 is 1.5. 0.4 plus negative 0.1 is 0.3. Negative 0.6 plus 0.2 is negative 0.4. The network just keeps layering addition on top of addition, billions of times over to generate a response.
Finally, Section 6, PyTorch and tensors, looking at some actual code examples. Now obviously, engineers don't calculate all this by hand. They define their inputs as what we call tensors. Here, tensor A is 3.0, 2.0, and tensor B is 1.0, 4.0. From there, PyTorch handles all the component-wise math automatically. A plus B prints out a tensor of 4, 6. A minus B prints out 2, negative 2. Scaling A by 3 outputs 9, 6. And multiplying A by negative 1 prints negative 3, negative 2. It perfectly automates the exact numeric results we computed manually at the very beginning of this explainer.
Which brings us to our grand finale. We've seen how these models combine, shift, and scale meaning using basic arithmetic. But here is the massive question I want to leave you with today. If basic addition and multiplication can encode language and position so elegantly, what happens when a model needs to compare billions of these vectors to see how similar they are to one another? How does attention actually work? Well, that requires an entirely new operation, the dot product. And that is the next mathematical secret behind AI, which we will definitely be uncovering in our next explainer. Thanks so much for learning with me today.